Let's talk about uh, equations. It is the kinematic equations, but under the condition that acceleration is constant. Okay, so we'll talk about those equations. These are the equations we are using for the case when the acceleration is constant. So this is the important part. Okay, let's go over briefly. So in this case, say x naught is initial displacement. The object is there. Okay. After time t, after time t, the object will be at position. Okay. So x final is the final displacement. Let's assume at position that initial position, and this is the final position. Let's say v naught is the initial velocity. Okay, at that point. Now let's say v or v final, both symbol you can use that. So v is the final velocity at this point. Now we can say delta x is the difference between x final and x initial. So these are the symbol key I'm using for this figure. So I'm assuming here the acceleration A throughout the motion is constant. Constant means any value. This is the key part here. Under these situations, we can write following equations. We can use following equation, which we can write V equals V naught plus A times T. V is the final, V naught is the initial, A is the acceleration, and T is the time period. Okay, sorry, time, not the time period. And other equation we can use is x. It's x. So basically, we can write x or x final. They are the same thing. Equals x initial plus v naught times t plus half at squared. The second equation we can use like this. The third equation we are frequently using is v squared equals v initial squared plus 2a x minus x initial. So these are the three basic equations we are using for the motion along a straight line. So it could be x-axis or it could be y-axis. Okay, but these equations are for the motion along a straight line. Let's use one of these concepts in the following examples. Say, in this example 1, we say the drag star can achieve average acceleration of 26 meters per second squared. Okay. So let's draw a sketch for that. It starts from rest. Say the object starts from this position. For simplicity, I choose origin at this point. If I choose origin here, my x initial will be 0. After time, t equals 5.56 seconds, the object is here. Okay. So my x final is this, or I just write x, that I want to find. But they give you the acceleration is 26 meter per second squared. I choose x initial is equal to 0. I want to know what is x final. They give you time 5.56 second. And what else? Start from rest. So V initial will be 0. So now let's see which equation we can use to solve this problem. So if you look at the set of equations, I believe that this second equation may be useful. Third one may not be useful because we don't know what is V final. Okay, so let's start with that. X equals x naught plus V naught times t plus half at squared. Here, this is 0. P initial is also 0 times t plus half. Acceleration is 26. I just write the number. And time is 5.56 squared. So these two are 0 plus 0 plus, if I do little algebra, that will be, let's see, it will be 402. Okay, so x final will be 402 meter. But be careful, if you are using any of these equations, x naught should be measured in meter. Okay, the acceleration must be measured in meter per second squared. If time is given in other unit, then we have to convert to seconds. We need this. So we need to convert at first in this unit. So this is one of the example of using one of the equations of the equation of a straight line, the equation of motion. We can use those equations to solve this problem. So you can follow exactly same process, some like the steps to solve this problem. Similarly, for this problem.